2.6 is a straightforward section, really. It talks about higher order derivatives. So not only the first derivative, you could take the second, the third. We're going to make main use of a second derivative. This is as far as we're going to go, but here we're going to practice a bit more. You know, they have applications, but we're really going to touch on that. These are the notations of different derivatives. This is Newton's. This is Leibniz. We really have to go this far. This is something else, this differential equation. This, you know, no need to worry about that. But y double prime, if you want to write a second derivative, sometimes the book write it this way. You just need to recognize it this way. You're welcome to write a second derivative like this all the time. A third derivative could be written this way, right? So you only need to focus on those two. So a second derivative is the second derivative of y with respect to x squared. You could write that as y double prime if you like. No big deal. It's the same thing, but you need to recognize what that is. So if I look at the first set of problems, I forgot the page with all the excitement. That means I'm going to have to... Page 142. Page 142. So, and if we weren't using the application for this, I wouldn't have covered it, but we need it. So the more practice we do, the better off we are. Find the second derivative. It's fairly simple for polynomials. If I take a derivative, that's 4 plus 0, so it's 4. And the second derivative is derivative of a constant is 0. Done. That much. And if I take a derivative of number 6, alright, well, I know I take a derivative of that. Bring the power down, subtract 1 from the power, negative 5 over 4 times 4x cubed plus, okay. Bring the power down, 3 times 2, 6x minus 6, and those 4's cancel out. And if I take a second derivative, that is negative 5 times 3 is negative 15. X squared, derivative of 6x is 6, and there it is. Quotient rule is a bit of a challenge, except this one we can manipulate a bit. If I take the first derivative, that would be 5 over 6. Bring the power down, subtract 1 from the power. So the first derivative is actually, what is that? Negative divided by 2, that's a 3, divided by 2, that's a 2. 10/3 t to the negative 5. And if you take another derivative, negative times a negative is going to be a positive 50 over 3 t to the negative 6. Or I could just say that is 50 over 3 t to the 6. That will work. So again, we're not doing much with those. We're going to do that 2 sections from now. For now, we just need to find it. The quotient rule is something else. I am gonna push this up because I need a lot of space, and that turns out to be perfect. So let me move that to the left a bit. Oh boy. Okay, I'll tell you what. There we go. Okay, now I gotta be patient with this. It takes a while, and those are not going away. So 3 types of problems we deal with mainly: polynomials, rationals, and radicals. Radicals are coming up. So if I take a derivative of the top times the bottom minus the top times derivative of the denominator, or over the denominator squared. So the first derivative is negative 4x plus 12 minus 1 plus 4x all over x minus 3 squared. The first derivative is 11 over, oh look at that, x minus 3 squared. Now, if this is what I get, Now I can get around it and say, you know what, wait a minute. I know that's 11 into x minus 3 to the negative 2. That saves me quotient rule on the second derivative. If I take the second derivative, that will be negative 22. Bring the power down, subtract 1 from the power. So that would be negative 22 over x minus 3 cubed. And there it is. Otherwise, I would have had to use quotient rule. Again, it's not hard, just long and a bit tedious. Just bear with it and it's fine. Here's a problem. Find the second derivative. So again, the reason I'm not focusing heavily on this chapter, we need the second derivative only for most of our applications, and I don't need you to go through the math of that. We just want to go for what applies to us. This says find g double prime evaluated at negative 1. Well, let's find g double prime first. First derivative. Bring the power down, subtract 1 from the power, times the derivative of the inside. Remember the chain rule? When do you apply the chain rule? Every time you take a derivative. And here comes the tricky part. You could clean this up. You could say those are 2 multiplied. When I take the second derivative, the 4 I leave out of it. It's going to be derivative of the first. Bring the power down, subtract 1 from the power, times the derivative of the inside. That's the derivative of the first, times the second. Plus the first is x squared plus 3x cubed times derivative of the second, which is just a 2. Now, if I'm evaluating this at a value, there's no need to clean it up. Cleaning it up is what takes most of the time. Plug the negative 1 in and simplify. 3 and negative 1 is 1 minus 3 squared. And negative 1, that's 2 minus 3, which is 1. 2 minus 3, which is 1. Again, since I'm evaluating, and negative 1 squared, that's 1 minus 3 squared times 2. There. No need for us to clean it up and do all of that busy work. Just plug it in and deal with numbers. Isn't that negative 2 squared, which is 4 times 3, that's a 12 times 1 times 1, plus, isn't that negative 2 squared, which is 4 times 2, that's an 8. So what is that? Isn't that 4 times 20? Isn't that 80? So I could say find the second derivative and evaluate it at values. And you notice I'm focusing on the second derivative more than anything. Here's a problem that says find the fifth derivative. So I'm given the second derivative to be, and if I write this, isn't that x minus 2 to positive 1/2? If I take a derivative of that, the 4 you leave alone, bring the power down, subtract 1 from the power, times the derivative of the inside, but that's a 1. So this is actually twice x minus 2 to the negative 1/2. If I take the fourth derivative, bring the power down, 2 times negative 1/2 into x minus 2, subtract 1. Negative 1/2 minus 1 is negative 1/2. And wouldn't those cancel out, and you're left with a negative x minus 2 to the negative 3/2. And how about a fifth derivative? Bring the power down, negative times the negative is a positive, and that's x minus 2 to the negative 5/2, which is 3 over 2. Isn't that the square root of x minus 2 to the 5th power? And that's all we want. Just a bit of practice of second derivatives and third derivatives, and we're going to use those heavily in the sections to come.